I kind of want to do. I think we should do this one.
We can probably ask him for two and just do questions.
All right. So
4.19 is the one in 5.
0.18.
by the way, did you all see I know they put up that problem that I messed up on you? I'm sorry about that.
You said homework 19 though, and I didn't see any problems for
What's that?
You said homework 19 when you posted that. Like the
There's nothing
tab.
posted on there?
It was just the
It's just a question we did.
the question that you reviewed.
Oh, yeah, but I mean, well, you had homework related to, you had.
Amper's law.
We had Amber's,
Yeah.
Ampere law.
Yeah.
but not.
Questions?
Can we do 4.18?
Yeah, I think somebody else asked me about this just a second. So, I mean, isn't that the one we just did?
You had an answer from before.
All right, go ahead.
Given a 2 centimeter radius solid wire centered on the z-axis.
So we've got radius, 2 centimeters, and it's solid, and it's in, right? And you have current density, J going up.
Yeah, J equals 3 rho A over centimeter squared
3 rho, and it's what?
over centimeter squared.
Amps
Oh,
per.
yeah, amps per
All
centimeter
right,
squared.
So I'm gonna just multiply this by 10 to the 4th, and make it amps per meter squared in the opposite direction.
Yeah.
It's a good mark.
And then plot the magnetic field intensity H versus the radial distance from the z-axis over the range 0 to 8.
Pay attention to this, everyone. Pay attention. So, if you look at this, there's 2 regions. The rho less than A, call that region 1. And here, the integral of H dot dl around a closed loop is equal to the integral, well, the current enclosed in this case is going to be J dot ds. Does everybody follow me on this formulation? So, if you take a look at this, and I come out a distance here, rho, and I put my little Amperian loop here, I'm going to see that the H field is going to be a constant in terms of its magnitude at a given function or given radial distance. It's only going to be a function of radial distance. Do you all agree with that? It's in the phi direction. How many see that? All right, so now, I know that. I come down here, and I say, well, the integral of H dot dl, this is really just going to be the perimeter of the loop to the circumference, which is 2 pi rho. You all with me on this? I could write the formal form. I just prefer to put 2 pi rho, and it would be times H phi. Over here, we have to put the actual expression for J in there, and we have to do the integration. So we're going to integrate double integral. J here is going to be 3 rho times 10 to the 4th. And that's amps per meter squared in the AZ direction times the differential surface. The good thing to think about is if you look right down the z-axis, when you think what the differential surface is, well, it's going to be the distance d rho radially, and this distance is going to be rho times d phi. You all follow me? That would be the differential surface area, right? How many see this right? It would be in the AZ direction. So this would be simply equal to, I'll just put it this way, rho d phi. And I'll prime rho because we're going to integrate that out. And it would be in the AZ direction. So if you look at this, rho prime, if I'm inside there, goes from 0 to rho. And phi goes from 0 to 2 pi. You all agree with this? It should be clear, right? Yes, sir.
Just so I don't get confused on this, because in the answers, he didn't do rho prime separately from the row that was already in there. He kind of just combined all the rows together. Is that okay to do in a case like this?
Well, we're engineers, right?
Right.
So if it's me and I don't have to get in front of people and I'm doing this on my lonesome, I ignore that. I do, but technically you're not supposed to have anything in the kernel of integration inside the integral that has a limit function in here, right? that's a no-no. So that's the only reason we prime it, because you're gonna integrate that variable out and evaluate it. Yes, sir?
You would prime that other row that's next to the free.
The what?
There's another row that's next to the free. That would be.
Oh, yeah, this is prime two. Yes, I'm sorry. You're absolutely right. I'm sorry. You're absolutely right. So if you look at this right here, what I'm gonna do is just say, well, this integral will become, I'm gonna do the d phi integral. Well, az dot az is, when I integrate d phi, I get phi evaluated from 0 to 2 pi. It's just 2 pi. I'm gonna take all the constants out in front, so it's gonna be 3 times 10 to the 4th out in front. Now, when I integrate rho prime squared, because there's two of them, you can just put rho there if you want. I'm not gonna take off points if you don't prime it that way. So if you get rho squared d rho, that's rho cubed over 3. Do you all agree with that? When I evaluate that from 0 to rho, it's simply gonna be rho cubed over 3. And that will be equal to this 2 pi rho h phi. Now this is pretty straightforward if you look at this. One thing I'm going to do next is cancel the 2 pi's. Everybody follow this? So if I cancel the 2 pi's, I have the luxury of just taking an eraser to do that. I got a rho there, I got a rho cubed there. Makes that rho squared. And that would be h phi, and my h phi is going to be in amps, amps per meter. All right. He has it in amps, I think, per centimeters, doesn't it? I don't remember. It's a factor of 10 to the 30. Okay, you all with me on this class? And that's true from 0 to a. Now, once you get greater than that, for rho greater than a, now the integral of h dot dl around the closed loop will be the same as before. But over here, we'll go from 0 to 2 pi, just like before. But now our limits radially are from 0 to a, because that's only where the actual current exists. It doesn't exist outside it. Y'all follow me? So that's all the current that's enclosed by that loop. That would be the current density, which is 3 rho times 10 to the 4th. Az dot, and this is going to be rho d phi. Now, I didn't prime them right there, but you can prime them if you want. It doesn't matter, it's going to integrate out. Do y'all follow me on this? So if you look at this, over here we're still going to get 2 pi rho h phi. Now, this is all the current inside the loop, so it's a singular value. You're going to have 2 pi here. Then we integrate times 3 times 10 to the 4th. Just those constants, az dot out. And then you're going to have rho squared integrated to be rho, which is rho cubed over 3. So it'll eventually become a cubed over 3. And now, just modifying this. Does everybody follow me on this one? Same as before, only now we got a hard limit at a. Take a look at this, my h phi here comes to 2 pi's cancel, and I get 1 over rho. The 3's cancel, then I get 10 to the 4th a cubed amps per meter outside there. Now, I will ask you to sketch plots of whenever you do a calculation like this, to make sure you understand what's going on. So if you sketch that versus rho, and here's a, and this is h phi. Well, you can see this is going up as a square of the radial distance. So it's going to look like this. It starts at 0, goes up. It's going to hit a max here. And then it's going to start falling off as 1 over rho over here. You all agree with that? And the peak value, the value at the transitional point, you would put rho equal a, and that means you would have a squared times 10 to the 4th as the value right here. So the peak value would be a squared, and that's times 10 to the 4th. Does that make sense, everyone? And that's it in a nutshell. Almost all of these Ampere law problems, there's one exception I'm going to do. There's a couple exceptions. are based on basically some sort of a cylindrical coordinate system.
What happened to the factor of 3?
Pardon me?
I'm confused with the factor of 3. Okay.
It's in the statement of the problem you put it. For all, you could just make that K, have it as an arbitrary constant. Yes?
Where does the 3 come from for the row is?
Well, when you integrate, if you look at this, I have rho times rho is rho squared, right? Rho squared d rho integrated is rho cubed over 3, isn't it? X squared dx integrated would be x cubed over 3. That's where it comes from. I'm not sure if that's what you're asking or not, but the 3's are basically either due to the integration or the actual definition of the problem. Does that answer your question? Yeah.
Wait, so the only things that really change in these problems are if it's a pipe or a solid
Well,
wire?
J, right?
The-
If you
the
have,
J's
the current density can be defined by the problem statement. It can be something you have to calculate based on the definitions. Like if they say all the current flows between A and B in a radial distance, you would have to take that I and divide it by the area, which would be pi b squared minus pi a squared. That would be the current density. You all follow me on this? Now you get J that way. And you always remember when you're doing these problems, if you understand what Ampere's law is really saying, just have the loop. Everything that penetrates that loop, all the current, is going to be what you use to calculate the H field. Now, if there is no current inside of the loop, if it's cylindrically symmetric, then the H field's 0. Okay. Let me get to your questions and stuff. I want to do a problem, and I think it's the last problem in this section, and it has a toroid. All right, this is a good problem. I just got done talking to John about this in my office, because it is in my opinion, one of the better problems that aren't typically covered in physics books. Sometimes, maybe. Okay. So I don't know the problem number, but it's a toroid, and it looks like this. They have a toroid, and it looks, basically, you just got a core like this, and you have an inner radius A and an outer radius C. All right, doesn't matter what they are, but they're going to wrap this thing with a whole lot of turns of wire. So in here, you're going to have all these turns of wire like this. Think of it like a transformer kind of deal. And you're going to have this wrap, all evenly spaced. You're going to say there are n turns on this board, this toroid. And each one of these turns carries a current I, so there's going to be a current. Y'all follow me? Take a donut, just wrap it around with a whole lot of turns of wire, and put a current through that. That's actually, well, this is something later, but that's a common mode of chauffeur. So if you do this, now we're going to break this down. You all agree it's cylindrically symmetric looking down the z-axis, right? So we're going to be the plane of the board. This thing's centered about the board. Now if you look at this, I'm going to put this. I'm going to say I really have something like this. I have a whole bunch of cut wires. I'm going to cut this thing right down the center and try to imagine it. And basically out here, you're going to have all the current into the board. I'm just trying to show you that there's n turns. And what I did is hack this thing right down the middle. And each one of these has a current I coming out of the board. I hope you can appreciate this. I'm trying to draw it in a way that makes sense. Y'all with me? Now, effectively, what that does is it has a current of n times I flowing out of the paper inside, if you're between here and here, right? So if you take a look at the regions, if we're going to find HV, the first region would be for the radial distance less than A. Now what that is, here is, I'm at a distance rho, and it's less than the actual radius A. This is radius A. Y'all follow me? Can everybody see this and understand what I'm trying to do? Well, if you look at this, think about what that law says. And this law says integral of h dot dl around the closed loop is equal to the integral. Really, I can just put here, I might as well just make it simple. Just the I enclosed by the loop. That means how much current penetrates the loop. So here's my area that I'm talking about. And can everybody see no currents penetrating? So without even doing anything, you don't have to do anything more than that. It's just HV is 0 for this region. Now for the second region, and this is where rho is greater than A and less than C. And he does use C here because he has a mean radius between A and B, but you don't have to worry about that. Now here, this is the one you pay attention to. Now I'm basically at this range. Right? Can you all follow me? Now if I put my Amperian loop around here, I still have to do the integral of h dot dl around the closed loop. But now the current enclosed, there's n times I. Do you all follow me in there? Because you cut them right down the middle. There's n times I. And that means, well, this will always be 2 pi rho hv. This is n times I. Means hv here would be equal to ni over 2 pi rho. And that would be amps per meter. So that's what it is between 0 and C, or between A and C. Y'all follow me? I'm going to say this right here. Okay? Now, what is it when I get outside there? Now, if I'm like this radial distance, we're now I'm going to have rho greater than C. And I talk about the integral of h dot dl. Around that closed loop is the I enclosed. Well, how much current's flowing through there? And this is the thing you have to appreciate. All the currents flowing out of the inner one is flowing back in the outer one. You all follow me on that, class? So the net amount is 0. So over here you have 0, which means HV for this condition is 0. He asked him a problem to evaluate it at a radial distance B between A and B. I don't care about that. I mean, I might ask something where you'd have to evaluate it at a certain point. But what I would do is, and I'll ask this, is ask you to plot that versus radial distance. So if you plotted HV versus radial distance, it is 0 until we hit A. You all agree with that? At the point we hit A, it goes up, transitions to this value, the Ni over 2 pi A. That will be the peak value. So then it goes up here, it's Ni over 2 pi A. And then it asymptotically moves downward until it gets B, and then it goes to 0. That's how the H field would look inside of that toroid. Do y'all follow me, class? It's kind of important to appreciate that, because you're going to see you're going to do a whole lot of problems where you have long cylinders, toroids, things like that, and they're going to ask for you'll need to calculate the H field, the B field, eventually the magnetic flux, and other things that we'll get to in a bit. But you have to have an appreciation for these geometries and how to expose or really identify the symmetry and use it to calculate the H field. Now, do you have another question?
It was about the bounds on the graph, but that answered my question.
All right. I wanted to cover a couple of things today. Now, we're in chapter 4, and most of this stuff you remember, at least from physics. Everything we've done so far, except transmission lines, we've had in physics. Pretty much. Might not have the actual geometry, but you've had this. So now we're talking about a couple other things. I'm going to do this in a way that's going to be meaningful to you. The first is, I'm going to talk about B, the magnetic field intensity, which is whatever meter squared. And I'm going to talk about
integral over the J.
theorems that are useful. Now, I'm going to try to make sure you see how this parallels with what went on when we did electrostatics. This room's a little better today, but it's still kind of good. All right, so let's do it this way. You remember that you had the integral form of Gauss's law. It says the closed integral of d dot ds over any surface was equal to the charge enclosed by the surface, right? That was Gauss's law in an integral form. I'm going to remember that. Now, that's a very important law. It parallels Ampere's law. Ampere's law is the integral of h dot dl around a closed loop is all the current. Very simple. The differential form of this is divergence of D is equal to rho V. Now, this mathematically is the differential form of this. If you wanted to prove this, there's a lot of things you could do. Well, the Q enclosed would be actually the volumetric integral of rho, right, over the volume. Or the volumetric integral of divergence of D over the volume, which by definition is the integral of D ds over the surface. But I don't want to worry about that. So now, in magnetics, we just had the integral of h dot dl is equal to really the I enclosed by that. Y'all follow me? All right. Stokes' theorem says that this integral, because it's a contour integral, can be rendered as the curl of h dot ds is the same thing as that. That is, in fact, the integral of h dot dl over the closed loop, and it's also equal to the integral of j dot ds over the surface. Now, I'm doing this for only one reason, so you see the parallels. What it really means is that J, the current density, is simply equal to the curl of H. And you can see, here we have the differential form of Gauss's law. This is the differential form of Ampere's law. That's the way I say it. They're going to say use Stokes' theorem to prove. You don't have to. That's it. So if I gave you an H field and you wanted the current density, you would simply do the curl of it, which is a lot easier than doing integrations 90% of the time. The curl is defined in the back of your book at the last, it's on the cover, the last, back there. You all see this? Just open your book for a second. If you don't have it, don't worry about it. But there are three things defined. There's the divergence, there's the curl, there's the Laplacian and the gradient. Actually, the last one is Laplacian, but do you all see that? The curl? And you've had curl before in your mathematics courses. I will give you the curl if you talk about, the definition in cylindrical and spherical coordinates, but you should know the one in Cartesian. Anyway, so I just wanted to mention that. That's Stokes' theorem. It's on page 236. And it's not really a big deal, in my opinion. The next thing, we're going to talk about the actual, how you relate. You remember how in electrostatics over here, we related the actual value of V was equal to epsilon E. Remember that relationship, class? Related the D field to the E field. D field is going to be coulombs per meter squared. E field is volts per meter. Well, there's something that parallels that in magnetics, in magnetostatics, and it's that the actual value of what we call the B field is mu times H. Now, mu itself is called the permeability, and it's equal to mu zero times some mu relative. Just like we had an epsilon relative, you have a mu relative. The permeability, mu zero, is equal to 4 pi times 10 to the minus 7. And this is going to be Henries per meter of the unit. So it's in here. We'll talk more about this. You've been exposed to this, I'm sure, in physics. Right? Now, the permeability is something that's important to at least appreciate. I told you something about epsilon and materials. Do you remember one of the things about epsilon that was important? Well, the units themselves, you're right, farads per meter, but the one thing about epsilon, as engineers, you should appreciate, is the larger that value, the greater the energy storage capability is. Remember, the energy density, if you talk about the energy density in the electrostatic field, is 1/2, and it's going to be E dot E, or 1/2 epsilon times magnitude of E squared. Now, I don't want to spend too much time on this, but that's the energy density. That would be in joules per meter cubed. You remember this? Somebody do? I talked about it. All right. Now, for a given capacitor, you've got two plates. You put a voltage between the plates. You're going to have an electric field that's defined simply V divided by the distance that separates the plate. Do you all follow me on that? If you look at this, as epsilon goes up, the energy density goes up proportionally. So if you have a given geometry, and it's filled, a capacitor, it's filled with air, you're going to have so much. But as you increase the value of epsilon, that dielectric, the energy goes up. If epsilon increases by a factor of 10, the energy storage capability goes up by a factor of 10 for the same geometry. With magnetostatic stuff, the value of mu has to do with energy density. In magnetostatics, the magnetic energy density is 1/2 mu times the magnitude of H squared. It's really actually equal to 1/2, and they do it this way, B dot H. Well, I gave you B up here, so if you do the dot product, you get mu out front. Now that's energy density. The thing you see clearly is, yep.
Is there a reason it's 1/2 S on E on that side and H on that side?
Well,
They're parallel.
I'm talking about,
Well,
both
is
of
it-
them are in joules per meter squared when you do the math.
Oh, wait, no, I got it mixed up.
I mean, this is, E is volts per meter, right, volts squared,
Yeah.
meter squared, over meter squared. Epsilon is farads, right, per meter. If you do the math on this, what you're going to end up is getting what? Joules per meter cubed. Over here, you get joules per meter cubed, because it's going to be amp per meter, amp squared per meter squared, times mu, henries per meter. You're going to get a density that's going to be a joules per meter cubed. Same thing. As far as, but we can talk about that later. Now, that's energy density. So what it's saying is mu is something that has to do with different materials. And the way I like to think of it, it has to do with the ability to store energy or concentrate magnetic flux. Now, there's more to this, but I'm giving you a very simple overview. You know what transformers are? Iron core transformers. Iron core transformers they're basically laminated iron, but the mu value is over 1,000. Do you all know about, I mean, you've had this before, right? You've had power. I mean, you had power to gross go over all the different, I mean, how come it's important to have a large value of mu?
In the insulating.
I don't know if we went that deep into it.
All right, well, it really allows more energy to be concentrated. There's more to this that we'll talk about. But remember, both of these two things fundamentally tell you the energy storage capacity of, you might say, a volume of space. Just go with me on that one. That's the relationship. Now, there's something else we talked about with the B field. And that is something called the magnetic flux. I'm going to erase this right here. And I think you'll appreciate this. So, when we talked about the electric flux that penetrated a region, it was the integral of B dot ds. That's electric flux. Magnetic flux. The symbol we use is this. And it's equal to the integral of B dot ds over a surface. Now this is important, I'm about to show you. Now, since that's the magnetic flux, this would be in Webers. The B field is in Webers per meter squared. If you look at this for a second, you know, you're always probably asking yourself, why do we care about this? Because this is going to be used to calculate not only the energy in a region, or we can, but also the actual inductance of regions. You all have heard of inductance, and you know what that is. So when I talk about this flex calculation, it's important because from this we can get the inductance, the self or mutual inductance of any fluid. So the classic thing they do is I say, if I have a current I flowing here in the z-axis, and it's infinitely long, I try to make things as simple as possible at the beginning. And then I come out and I put a loop over here. Say the loop has a height h, and a width w. So this is w. And I'll say it begins, it's in the plane of the board, and this distance here will be a. What I want to do is find the amount of flux that penetrates that loop. Do y'all follow me? That's the idea. Now we're going to see in a second, once you do that, you want the mutual inductance between the two, an infinitely long wire in that loop. We just divide by the current causing that flux, and we get the inductance with the mutual inductance. So just bear with me on this one. Over here, to do that integration, this is kind of an interesting problem. And I have stories I can tell you about why this is interesting. Not right now. Well, the first thing I have to do, at a given radial distance rho, I have to find the H field. The H field will be I over 2 pi rho in the A phi direction. That would be going into the board, right? So, you all agree with that? The H field's going into the board. So from the H field, I can get B by multiplying it by mu. We can assume it's mu 0. So this integral, for that problem, becomes the magnetic flux is equal to the integral. It will be a double integral of the B field. Well, B would be mu 0I over 2 pi rho in the A phi direction. Now I need to dot that with the differential surface right here. That differential surface, just follow me on this one, guys, because people mess this up. Well, the differential width this way is simply d rho. Does everybody agree with that? The differential on this direction would be dz, and the sense would be a phi, because the normal to that would be in the phi direction. How many see this way? So if we come over here, we'll just write this down. I can do it right here. This is going to be equal to d rho times, and then it's going to be dz, and it's going to be a phi direction. And we're going to integrate rho. Well, z will go from 0 to h, so that's a trivial integral. Rho is going to go from a to whatever my outer distance would be, which would be a plus w. So rho here will go from a to a plus w. Y'all agree with that? As far as limits and everything, you all appreciate this. This is straightforward as it gets. But I take this, the a phi dot a phi goes away. Then I do the integral and I find the magnetic flux to that loop would be equal to mu 0 over 2 pi. Then I integrate, I'll do the dz integral first, which is z from 0 to h is just h. And then when I integrate the 1 over rho d rho, I get an actual log from the outer part, which is a plus w, to the inner radius, which is a. And that would be, it's got a current times I in there, so it's got to have I in it. That would be the flux, and the units would be Webers. That's it. Now, you've probably seen stuff like this before in physics, for sure, and maybe some of your other classes. That's the magnetic flux. The mutual inductance between this current element and this loop is just the magnetic flux penetrating the second circuit, or that loop, divided by the current causing the magnetic flux. So that means the inductance of this is just mu h over 2 pi, natural log of a plus w over a. Y'all follow me on this, class? I have a question for you. What happens if this is not just one turn, but there's 2 turns of wire on top of each other? Say it's shellac wire. what would happen to the inductance, do you think? Anybody? We doubled, right? 3 turns, triple, 4 turns, well, by factor of 4. N times the number of turns would be the mutual inductance in that outer loop. Do y'all follow me on this? It's proportional to N. Now that's the mutual inductance. I don't have time to go through self-inductance today because you have a quiz. But I try to make this as simple as possible. So do me a favor, spread out at least 1 decimal.